In our previous lesson, we had explained merge sort algorithm. Now in this lesson, we are going to analyze merge sort algorithm. We will look at various properties of merge sort algorithm. We will try to see how efficient it is in terms of time and space complexity. Some of the properties of merge sort algorithm that I want to talk about are, first of all, merge sort falls in the class of algorithms that we call divide and conquer algorithms. In divide and conquer strategy, we break a problem into sub-problems, and then we first find out the solutions to sub-problems, and from solutions to sub-problems we construct the solution of the actual problem. Second property of merge sort algorithm is that it's a recursive algorithm. Programmatically, recursion is a function calling itself, but in general, recursion is reducing a problem in a self-similar manner. Merge sort is also a stable sorting algorithm. When we explain a sorting algorithm, we try to sort a list of integers in increasing order of value, but a sorting algorithm can be applied to a collection of any data type. When we are sorting complex records, we sort them on the basis of some property or some key. For example, let's say we want to sort points in Cartesian plane, where each point is given as a pair of two integers with x and y coordinates, and we want to sort this list in increasing order of x coordinate. So the key here is x coordinate. For this list there can be two possible sorted arrangements. We have two records, 2 points that have equal x coordinates. So in the sorted arrangement, either of these could come first, but in a stable sorting algorithm, the relative order of records with the same key is preserved. So if 2,5 is occurring before 2,3 in the original list, 2,5 must also occur before 2,3 in the sorted arrangement. Merge sort is a stable sorting algorithm, so it preserves the relative order of records with same key. The next property that we want to talk about is merge sort is not an in-place sorting algorithm. An in-place sorting algorithm takes constant amount of extra memory to sort a list. Previous sorting algorithms like bubble sort, insertion sort, and selection sort, all of them were using only some temporary variables to store indices. The extra space taken was not dependent upon the size of the list, but in merge sort, when we divide an array into sublists, two sublists left and right, we create two entirely new arrays. So definitely the amount of extra space that we will take will be proportional to the size of the list, the number of elements in the list. The space complexity of merge sort is big O of n. In fact, we should say theta n. Technically, theta notation is what we should be using most of the time, but because big O notation is more famous, we use big O notation. What this means in simple terms is the memory or the space consumption is proportional to the number of elements in the list. The time complexity of merge sort algorithm is big O of n log n in worst case. Once again, we should be using the theta notation to be more precise. If you are not aware of big O and theta notations, we have a series on time complexity analysis. You can find a link to it in the description of this video. Let us now try to deduce and understand time and space complexity of merge sort. Let us first try to analyze the time complexity. We have the pseudocode for merge sort algorithm here that we had written in our previous lesson. Let's say the time taken for an array of size n by merge sort algorithm will be Tn. Let us now see how we can find an approximated expression for this Tn. Talking about some of the fundamentals of time complexity analysis, we always try to approximate the worst case, and we try to see the rate of growth of time taken for very high values of n, and then we try to classify the time expression as big O or theta of some common function. Here in this algorithm, let's say when we are executing for n greater than 1, all these statements, they are simple statements. Simple statements are statements that have simple operations like arithmetic or logical operations, assignments or comparisons, and simple statements execute in constant time. So let's say these set of statements, these set of simple statements in the worst case will take some constant time c1. If there are no loops or function calls and there are only simple statements, then the time taken will not be a function of the input size. Now these two loops, these two assignments here will have same cost, and these two loops together will run n times. So we can say that they will together cost us some constant C2. Let's C2 is the cost of executing one of these statements. Then the cost will be C2 into n. Sometimes we directly talk in terms of the asymptotic notations only, like we can directly say that this particular segment of the code is theta n in terms of time complexity. But let's talk like this, that this will execute in C2n, where C2 is some constant. And then we have this recursive call merge sort for left. If we are saying that we will take tn time for merge sort for an array of size n, then left will be an array of size n by 2. So this will be tn by 2 cost for us. And then we have another merge sort call that will again be tn by 2. And then we have a call to merge. Now for this one we will have to look at the merge function. What is the complexity of merge function? If you remember the merge function, all merge function was doing was it was picking up one element from either left or right at a time and writing it in another array. So in all, loops were running for total length of left subarray plus total length of right subarray. So in all, loops were running for n times. So if you would analyze the running time for merge function also, it will be of some form like some constant times n plus some other constant. I'm not going into all the detailed calculations here. So for n greater than 1, tn will be equal to 2 times tn by 2 plus we can add all these costs up. It will be something like this. If n is less than 2, or in other words, if n is equal to 1, that is the only case that we will have when we will go and simply return. In this case there is only one simple comparison and we return, so the cost will be some constant. We can simplify this equation further. Let's say this is equal to 2tn by 2 plus c dash n plus c double dash. Once again, c dash and c double dash are some constants. For very high values of n, this constant term c double dash will be negligible compared to c dash n. And in time complexity analysis, we are mostly worried about the rate of growth of function for very high values of n. So for the sake of simplifying our calculation here, we can get rid of this plus c double dash, and we can say that tn is equal to 2tn by 2 plus some constant times n for n greater than 1. And now we can try to solve this recurrence. Tn here is equal to 2tn by 2 plus c dash n. Now tn by 2 can also be written as 2tn by 4 plus c dash into n by 2. And of course we will have one more c dash n outside here, and this will evaluate to 4tn by 4 plus 2c dash n. Once again, tn by 4 can be written as 2tn by 8 plus c dash into n by 4, and we will have this 2c dash n outside, and this will evaluate to 8tn by 8 plus 3c dash into n. And we can go on reducing like this. We can write this as 16tn upon 16 plus 4c dash n. And if I have to write this in form of some generic k, this will be equal to 2 to the power k times tn upon 2 to the power k plus k into c dash into n. Now we want to reduce this in terms of t1 because that is what we know. In that case, n upon 2 to the power k will be equal to 1. That will mean 2 to the power k will be equal to n, and k will be equal to log n to the base 2. So if k is equal to log n to the base 2, we will have this expression in terms of t1. So finally we can write this as 2 to the power log n to the base 2 times t1 plus log n to the base 2 into c dash into n. T1 is equal to C, and 2 to the power log n to the base 2 will be equal to n. So this will be equal to nc plus c dash into n log n. And now if I have to write this term in terms of big O notation, then what we typically do is we drop the lower order terms. N is a lower order term than n log n. So for very high values of n, we can ignore this part, this nc, and we can drop the constants from this part to say that this is equal to big O of n log n. In fact, this will also be equal to theta of n log n. Theta of n log n here means that for some constants c1 and c2, Tn, which is equal to nc plus c dash into n log n, will be greater than or equal to c1 times n log n and less than or equal to c2 times n log n if n is greater than or equal to some constant n naught. And big O of n log n means that Tn will be less than or equal to some constant times n log n if n is greater than or equal to some constant n naught. So this function Tn here is both theta of n log n as well as big O of n log n. When we say that merge sort is theta of n log n, in practical sense we mean that the rate of growth of time taken by the algorithm for very high values of n is as close to the growth of function n log n as possible. And by big O notation in practical sense we mean that the rate of growth will not be more than the rate of growth of n log n. We will not go into all the details of why we safely ignore the lower order terms and constants and say that this is big O or theta of a particular function. It's beyond the scope of this lesson. Now let us try to understand the space complexity requirement for merge sort algorithm. I'll take this example once again that we had used previously to describe the algorithm. When we are talking about space complexity, we are talking about the extra memory that we will consume while executing merge sort. The extra memory that we will consume will mostly be in the form of these auxiliary arrays left and right that we will create. If you see, once the merge process has finished, we do not need these arrays, so either they can be cleared automatically if they are on the stack section of applications memory. Once the function finishes, they will be erased from memory, or we can explicitly erase them by writing some extra statements. But it's important, it's really needed that these arrays which are being used as scratch space are deleted at the end of the function. There can be one variation of merge sort in which instead of using these auxiliary arrays left and right, instead of using this extra memory for left and right sublists in the merge sort function, we can use extra memory in the merge function. But let's analyze our implementation only. First, think about this. Let's say we do not erase left and right at the end of merge sort function. So what will be the memory that we will consume? If you see here in this particular structure, we start with an array of size n, and then we split it into two arrays of size n by 2, and then we split it into 4 arrays of size n by 4. Let's call this level 0, and let's call this level 1, and let's call this level 2 where we have sublists of size 2 each, and let's call this level 3. For an array of size n, what will be the maximum number of levels? It's like at level 0 you have a list with n elements, and then you go to 2 lists with n by 2 elements each, and then you go to n by 4 elements each, and you go on like this till you reach sublists with 1 element each. Let's say this will take k steps, so it will mean that n upon 2 to the power k, we will need k divisions by 2 will be equal to 1. So k will be equal to log n to the base 2. So we will have log n levels after level 0, and at each step we will have, at each level we will have extra memory used to store n elements. 8 elements are there at level 0, and there are 4 plus 4 8 at 1, and there are 2 into 4 8 at 2, and so on. For this example, n is 8, log n would be 3, so we take 3 steps. We have L1, L2 and L3. So if we do not clear extra memory used for left and right, we will take space for n integers each for log n levels. So space complexity will be theta of n log n. The space requirement, extra space requirement, will be theta of n log n. Now if we assume that we will clear left and right arrays once we are done using them in the merge sort function, then to explain this scenario, I'll simulate the merge sort calls once again using this array as example. When we will make a call to merge sort passing this array, we will create these two sublists left and right, and then we will pause the execution of the first call and go ahead and make another call on the left sublist. Now for this call also two sublists will be created, and we will go on to first sort the left part, which will again create two sublists. Except this original arrays, all these extra arrays that are being created are using extra memory. Now once we reach this stage, we are not creating any extra sublist for these sublists with one element each. We will start wrapping up. We will merge these two, 2 and 4, and once the merge is done, we can get rid of the two arrays with one element each, and we can go on to sort the other half. So if we will clear the auxiliary arrays left and right once we are done using them, in the worst case we will use space for n integers at level 1. We will use space for n by 2 integers at level 2, and we will use space for n by 4 integers at level 3. And if we will have more elements, we will go on like this. So the extra space taken will be n plus n by 2 plus n by 4 plus we will go on in a geometric progression. For this example here, once we will be done merging this sublist 1, 2, 4, 6, we will clear the sublists created for it, and then we will go to the other side. So at any time at a level, we will use half the space that we would be using at the parent level. Let us now try to solve this geometric progression here. We can write this as n into 1 plus 1 by 2 plus 1 by 4 plus, and in all we will have log n terms in this geometric progression. But even if we take this geometric progression 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 and so on till infinity, if we take this till infinity, then the sum will be 1 upon 1 minus 1 by 2, which will be equal to 2. So overall this expression, if we call this function Sn, then Sn is definitely less than or equal to 2n, and Sn is definitely greater than or equal to 1n. So Sn is clearly theta n. So space complexity of merge sort is theta n. So this was time and space complexity analysis of merge sort algorithm. Thanks for watching.